Hello again. With this video we're going to begin a new chapter, a chapter material dealing with some basic ideas related to chemistry. So let's get right into it and start talking about the idea of matter and atoms. Now matter is anything that has mass and occupies space, and sometimes it's difficult to think about what mass is, and the way we think of it is that the weight that you have is mass measured in a gravitational field. If I went to some place where there was no gravity, I would still have the same amount of mass. I simply wouldn't have any weight. And of course, go to different gravitational areas and my weight changes. All right, so now let's consider what this matter is going to be composed of. It's going to be composed of atoms put together by chemical bonds. And we'll talk much more about chemical bonds in a later video, but some words are going to come up. If you hear the word molecule, then you know that you're going to be talking about any two atoms hooked together by a chemical bond. All right, any two atoms hooked together by a chemical bond, two of the same atom or two different ones. Now, if the word compound is used, now somebody is specifically talking about the idea of something being composed of different kinds of atoms or different kinds of elements. And we'll talk more about these chemical bonds in a future video. But when those words molecule or compound come up, realize that we're going to be talking about matter composed of groups of atoms attached to each other by these bonds. Now, what are some of the essential elements, or what are the key elements that we're going to find in living things? Of course, since this is biology, we're going to be focusing on the building blocks, the atoms that make up living things. CHNOPS, C-H-N-O-P-S, and make sure you get yourself a periodic table. Take a look at the information in your textbook also on some of these key elements or key atoms. And you'll want to be familiar with the names that are associated with these symbols, these letters. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. If I include calcium and potassium, then I'm talking about, 99% of what living things are composed of. Now, there are other materials that make up living things, but they tend to occur in very small percentages, 0.01% or less of the makeup of an organism like ourselves. Things like iron or manganese or selenium. They're important, but very small in abundance. Those are called trace elements. But those first six, in particular, CHNOPS, keep those in mind. We're going to be seeing those more than any other six. We're going to be seeing them over and over again. So you want to be very familiar with those six in particular. Now, what are these things called atoms? What are they composed of? What's their makeup? Well, we're going to find that they have three key component parts. Protons, that's the subatomic particle that we're going to find in a region of the atom called the nucleus, and it has a positive charge. The neutron, also a subatomic particle found in the nucleus of atoms, but now this one lacks this quality of having a charge. And we're also going to have electrons. These are subatomic particles, by the way, much, much, much lighter than the protons or the neutrons. And instead of being found in the nucleus, they're found in a region called the electron cloud, and they have a quality of negative charge. Now, the only thing that you want to be aware of in terms of this quality of charge is that we're going to repeatedly mention how oppositely charged things attract each other. And so you could think of the electrons and the protons as having an attractive force for each other. But notice that we've, in a sense, subdivided the different regions of the atomic structure in terms of where we find protons and neutrons and where we find the electrons. So, what were those regions that we just mentioned? The nucleus is the core of the atom. It's the dense central region of an atom that's composed of what? Protons and neutrons together in that nucleus. There is one element, hydrogen, that only has protons in its nucleus, but everything else has some combination of protons and neutrons making up their nucleus. Now, surrounding the nucleus is a region called the electron cloud, and it's an area of space, mostly empty space, where the electrons are moving very rapidly. You want to think of them as moving at close to the speed of light in that region called the electron cloud. And we're going to find out that that electron cloud actually has subdivisions within it, that there are electron energy levels or electron shells that make up that electron cloud that surrounds the nucleus of the atom. Realize this is our atomic theory. This is our model that we use to try to explain atomic structure. And what we talk about this semester in terms of atomic structure, realize that it is just a model. We're not trying to say that this is exactly the nature or structure of the atom, but this is a way for us to visualize it and try to understand it. Take a look at this illustration. You'll see what I was referring to before. There's our protons and neutrons that we talked about. Here they are located in the nucleus, that central dense region of the atom. And then in the area around the nucleus is the electrons. And notice there's two representations here. On one side, we see the electron shown moving in an electron energy level. And on the other side, this region is shown as a cloud-like structure, the area where the electrons are moving. So you don't want to think of those electrons as following a perfectly circular path. That's not the case. They're moving very rapidly within that region called the electron cloud. By the way, notice this helium atom that we're talking about here has a makeup that includes 2 protons in the nucleus, 2 neutrons in the nucleus, and then 2 electrons in the electron cloud. Later we'll be talking about those numbers and how they're used to describe the features or the nature of individual atoms. One of the ways we describe atoms is by using what's called the atomic number. When you take a look at your periodic table, you're going to see that for each element on the periodic table, they have an atomic number. And the atomic number is going to be, in a sense, the definition of that particular atom, that particular element. It's the number of protons that are found in the nucleus of that particular atom. So whatever the atomic number of an atom is, it defines for you immediately how many protons are found in the nucleus of that particular atom. Now, interestingly enough, the number of electrons that are found orbiting, moving around in the electron cloud of an atom are going to be a number that is equal to the number of protons that are in the nucleus. And notice in parentheses there I've put an undisturbed atom. That means an atom that hasn't been involved in any kind of chemical interactions or any kind of chemical reactions. But when you look at those elements on the periodic table itself, think of it as you're looking at them in their undisturbed state. So if I have a particular element that has an atomic number of 8, that means that there's 8 protons in the nucleus. I expect to find then 8 electrons in the electron cloud of that particular element. So atomic number gives me the number of protons, and it also gives me the number of electrons if the atom is in an undisturbed condition. Now, another quality that we're going to find associated with atoms is the idea of atomic mass. Now, the atomic mass, and sometimes you'll see people refer to it as the atomic weight, is going to be defined as the number of protons plus the number of neutrons found in the nucleus of a particular atom. So now notice this atomic mass number is going to be something that's a combination of the number of protons and the number of neutrons in the nucleus of an atom. Let's take a look at a couple examples. Here I've given you the atomic number of 3 different elements. So in this case, notice here, shown as a subscript, almost always drawn to the left of the letter used to abbreviate the name of the element. This is carbon, by the way. C is for carbon. And we'd say carbon has an atomic number of 6. So think about what that tells me about carbon. 6 protons in the nucleus, and that means that it should also have 6 electrons circling in its electron cloud. Next one, nitrogen, atomic number of 7. Third one, phosphorus, atomic number of 15. Make sure that you can take a look at least the first 20 elements on the periodic table. Find this atomic number and make sure that you review for yourself what that means. You don't have to memorize any of these, because anytime I'll want you to know something about the atomic number of an element, I'll tell you what its atomic number is. I just want you to know what the atomic number tells you about the element. So if I know nitrogen 7, that tells me 7 protons. It also tells me 7 electrons. Let's take a look at some examples of atomic mass numbers. Here's carbon again with its atomic mass of 12. Do you remember what its atomic number was? 6, right? So now remember what we said that atomic mass was. It's the number of protons, which we know is 6 from the atomic number, plus the number of neutrons. And so it looks like carbon has 6 protons and 6 neutrons. With nitrogen, its atomic number was 7. Does that make sense? 7 protons plus the 7 neutrons, giving me atomic mass of 14. Now, just so you don't think that the number of protons and the number of neutrons are always equal, take a look at phosphorus. It has an atomic mass of 31. If you remember from our previous slide, look what phosphorus's atomic number is, 15. So you see where I got the 16 neutrons? If phosphorus has an atomic number of 15, then 15 from 31 leaves me with 16 neutrons making up its nucleus. Remember, the atomic mass is the number of protons plus the number of neutrons in the nucleus. Well, take a look at this last one. I've given you the atomic number of sodium, Na is sodium, atomic number of 11. The atomic mass of sodium, 23. This is the kind of question that I would ask you on a quiz or a test, and I'd expect you to be able to tell me the following 3 things. Number of protons, number of electrons, number of neutrons. Take a moment to think about it and see if you have those numbers. Now, the atomic number, 11, tells me that there's 11 protons, and also I'd expect there to be 11 electrons. The atomic mass of 23 tells me that those 11 protons must be combined with 12 neutrons to make up the nucleus. So once again, take your periodic table, work with the first 20 elements up through calcium, atomic number 20, and make sure you can figure out how many protons, how many electrons, how many neutrons they have based upon their atomic number and their atomic mass. Please make sure you take a look at this and practice doing it. Now, there is one other way we can talk about some atoms, and it's an interesting feature of some of the elements in the periodic table, not all. There are some elements that have atoms that have the same atomic number, okay, but they have different atomic masses, which means they have different numbers of neutrons, doesn't it? Those are called isotopes. Isotopes. Not the baseball team, right? But the idea of isotopes clearly is associated with some qualities of differences in the makeup of the nucleus of atoms. Let's take a look at an example. Here we have the isotopes of carbon. There's carbon 12, carbon 13, and carbon 14. The numbers are their atomic masses. Now, since they're carbon, remember we said that the number of protons defines who you are. So if you look at this table here, you can see that in terms of the number of protons, all 3 of those isotopes of carbon have the same number of protons. But look at the neutron line. You can see the difference, can't you? Carbon 12, 6. Carbon 13, 7. Carbon 14, 8. So the different isotopes of carbon have different numbers of neutrons, but they have the same number of protons. Now, interestingly enough, some isotopes are radioactive, which means that their nucleus spontaneously breaks apart, decomposes, and releases energy. Not all isotopes are radioactive. In this particular case, think of it this way also. If we looked at the carbon dioxide floating around in this room, the CO2, we would find that the vast majority of the carbon would be carbon 12. And there'd be very tiny amounts of carbon 13 and carbon 14. Carbon 14, by the way, is the radioactive isotope of carbon, which means that if we watch that carbon 14, we're going to be able to see that it spontaneously, that means all by itself, its nucleus breaks apart into pieces over time, and in doing so releases energy. That means that if we have some carbon 14 and we can measure the energy it releases, and we know how often it goes through this process of releasing energy, pieces breaking off of the nucleus, you'll find that we can use carbon 14 as a way to date things. You may have even heard of people doing archaeological studies where they say, oh, we've dated this material using the carbon 14 method. So that's one of the uses we can make of radioactive isotopes. Oh, by the way, before we move to the next slide, notice the number of electrons right? Remember what we said? We'd expect in atoms the number of protons would equal the number of electrons. Okay? Here's another good example of that. How can we use some of those radioactive isotopes? Well, we can use them as tracers in biological studies. For example, what if I fed you some sugar with carbon-14 in it? Now, luckily, carbon-14 doesn't release energy that would be dangerous to you in terms of your cell structure or function. But as you eat that carbon-14 sugar, and if I could follow with, in a sense, a very specialized kind of Geiger counter, I could follow where that radioactive carbon-14 was going. I could figure out, how does your body process sugars? What happens to the carbon that goes into your body in terms of the sugars that you take in? In one of these illustrations, you can see that they've shown the presence of some radioactive material in the thyroid gland of an individual. Sometimes when people need to have their thyroid glands tested, what they'll be given is an injection or a drink that has radioactive iodine present. Now, the thyroid gland has as one of its functions collecting iodine from the things that we take in from the environment. And so it would be a way to determine how well is that thyroid gland working. Is it effectively taking in the iodine that went into the body? Also, as you might know, individuals might be placed into a device called a PET scanner, which is a positron emission tomography device that measures those small amounts of energy released by certain radioactive isotopes. And as a result, people can be tested in terms of how certain organs in their body, or their brain, for example, might be functioning in terms of how their body is using certain types of radioactive elements. So this is the primary way that biologists use radioactive isotopes. We use them as biological tracer molecules so that we can follow, gee, how's the body making use of that particular element? An interesting use of these types, these odd forms of elements. Now, think about what we talked about. We discussed the idea of matter in general, anything that has mass and occupies space. We said that that matter was composed of atoms. The atoms could be hooked together into molecules or compounds, and we'll talk about those more in the future. Then we talked about the two key numbers that tell us something about the structure of atoms, the atomic number and the atomic mass. Take a moment to think about what those told you. Okay, atomic number was what? The number of protons. It's also the number of electrons in an atom, in an element. The atomic mass, what was that? That, in a sense, was the nature, the structure of the nucleus, wasn't it? It was the number of protons plus the number of neutrons in a particular atom. Now, this is information that you're going to want to review. We're not going to go into a lot of additional detail related to this type of information, but it is important for you to have a basic understanding of this basic chemistry, inorganic chemistry, for us to understand the chemistry we need to use when we talk about living things. Now, in the next few videos, we'll be talking more about matter and atoms, why they bond together, how they bond together. So I look forward to talking to you about that in a future time.